Welcome back. In the previous episode, we learned how to use Terraform data sources to replace hard-coded values with information retrieved directly from AWS. Today, we're taking the next step. We'll learn how to write cleaner, smarter, and more dynamic Terraform code using expressions and built-in functions. Instead of creating a new project, we'll continue improving the one we've been building throughout this series. Let's get started. Today's episode is going to be mostly hands-on. We'll briefly introduce the key concepts, then jump into VS Code and apply them to our existing Terraform project. You'll learn how expressions work, how to build dynamic strings, how to use Terraform functions, conditional expressions, count for each, and locals. By the end of this episode, we'll transform our project from a static configuration into a reusable one that can deploy multiple EC2 instances with much less duplicated code. Right now our project works, but it's still fairly static. We have a single EC2 instance, several repeated values, and a configuration that doesn't scale very well. Our goal today is to refactor that project into something much more flexible. Instead of rewriting resource blocks every time we need another server, we'll let Terraform generate them dynamically. This is one of the biggest advantages of infrastructure as code. Before we start coding, let's remember the workflow we've been following throughout this series. We always begin with the official Terraform documentation to understand how a feature works. Once we understand the concept, we implement it ourselves. Then we use AI to accelerate our work, review our code, and discover possible improvements. Finally, we validate everything with Terraform FMT, Terraform Validate, and Terraform Plan before deploying. AI is an excellent assistant, but the official documentation is still our source of truth. Now let's switch to VS Code and start refactoring our project. We'll continue working on the same project we've been building throughout this series. Over the last few episodes, we've added variables, outputs, resources, dependencies, and data sources. At this point, our project is working correctly, and we have a solid foundation to build on. Let's take a quick look at the project structure before we continue. Here we have our main.tf, where our infrastructure is defined. Variables.tf contains all the input variables. Data.tf is where we read existing AWS resources. Output.tf defines the values we want Terraform to display after deployment. And finally, our tfvars files store the values for each environment. Everything is working as expected, but there's one problem. Our configuration is still very static. If tomorrow we need to deploy 3 EC2 instances instead of 1, we'll quickly start duplicating code. That's exactly what we're going to solve today. Before making any changes, let's follow the workflow we've used since the beginning of this series. We'll start with the official Terraform documentation to understand how expressions and functions work before writing any code. According to the official documentation, expressions are used to compute values inside a Terraform configuration. Almost everything we write in Terraform is an expression. Variables, references to resources, functions, conditionals, and many other features are all built on top of expressions. So let's see how we're already using them in our project. One of the simplest expressions is string interpolation. Instead of writing fixed values, we can combine multiple values dynamically. We'll use this in a few minutes to generate resource names automatically. Terraform also provides many built-in functions. Functions allow us to transform values, manipulate strings, work with collections, perform calculations, and much more. We won't cover every function today because there are dozens of them. Instead, we'll use a few practical ones while improving our project. Now that we understand the concept, let's see something interesting. Even before adding any new code, we're already using Terraform expressions. These may look like simple values, but every one of these is actually a Terraform expression. Terraform evaluates each one before creating the infrastructure. Now let's learn how to make these expressions even more powerful. This is an expression. Terraform evaluates this expression and retrieves the latest Amazon Linux AMI before creating the EC2 instance. This is another expression. Terraform reads the value from our variables and replaces it during execution. Here, Terraform evaluates a resource reference. Instead of writing the security group ID manually, it uses the ID returned after creating the resource. Even these tags are expressions. Each variable is evaluated by Terraform before the infrastructure is deployed. So, if everything here is already an expression, how can we make these expressions even more useful? Let's start with one of the most common features you'll use every day. String interpolation. Right now, our instance name comes directly from a single variable. If we deploy to different environments, the name will always be the same unless we change it manually. Instead of using just one value, we're now combining two variables into a single string. This is called string interpolation. Terraform evaluates everything inside the curly braces and builds the final value for us. In our case, the first value is the instance name, and the second one is the environment. Now that we've changed the configuration, let's see the result. We'll run Terraform plan and verify how Terraform evaluates this expression before creating or updating our infrastructure. Right now, our name is a little redundant. We already have dev in the instance name, and we're appending development again. In real projects, resource names should be meaningful, but also concise. Let's improve this a little. This looks much cleaner. Our base name stays the same, while the environment is added dynamically. If we later deploy the same configuration to production, the resource name will automatically become Terraform-demo-production without changing a single line of Terraform code. The plan looks exactly as we expected. Terraform evaluated our expression and generated a new value for the name tag. Let's apply the change and verify it in AWS. Here we can see the result. The instance name is no longer a fixed value. Terraform built it dynamically using the two variables we combined in our expression. This may seem like a small improvement, but when you manage hundreds of resources, dynamic values like this make your configurations much easier to maintain. String interpolation is just one type of expression. Terraform also provides many built-in functions that let us transform values before they're used. Let's go back to the official documentation and take a quick look at some of the functions available. As you can see, Terraform includes dozens of built-in functions. We don't need to memorize all of them. The important part is knowing they exist and understanding how to find them in the official documentation when we need them. Let's use a couple of simple functions to improve our project. Terraform is not creating a new instance. It will update the existing EC2 instance in place because we're only changing tag values. The environment tag is changing from development to development because we're using the upper function. The manage by tag is changing from Terraform to Terraform because we're using the lower function. The instance name remains the same because our string interpolation is still generating Terraform-demo-development. This is a simple example, but it shows how Terraform functions can transform values dynamically before they are applied. The upper function converts a string to uppercase. The lower function converts a string to lowercase. We don't need to modify the values inside our variables. Terraform transforms them only where we use the functions. Now we've used string interpolation and built-in functions. Next, let's look at conditional expressions, where Terraform can choose one value or another depending on a condition. Before writing any code, let's go back to the official documentation. A conditional expression allows Terraform to choose between two values based on a condition. The syntax is very similar to what you may have seen in other programming languages. If the condition is true, Terraform uses the first value. Otherwise, it uses the second one. Let's see a practical example in our project. Let's say we want detailed monitoring only in production. Instead of changing the code every time, Terraform can decide automatically. We won't change anything else in our project. The only thing we're changing is the condition itself. Now let's run Terraform plan again and compare the result. Our current environment is development, so the condition evaluates to false. Monitoring is already disabled, so Terraform doesn't show any change for that attribute. Terraform only includes values in the plan when the desired configuration is different from the current infrastructure. Now let's switch back to development and run the plan again. Terraform first evaluates the expression. Our environment variable contains development. The condition asks, is the environment equal to development? The answer is yes, so Terraform returns true. That's why monitoring changes from false to true. That's the power of conditional expressions. Terraform can make decisions automatically based on the values we provide without requiring us to modify the rest of the configuration. Conditional expressions are very useful when Terraform needs to make decisions. But what if the requirement changes? What if, instead of enabling monitoring, we need to deploy 3 EC2 instances instead of 1? We could copy and paste the resource block several times, but that would create duplicated code and make the configuration much harder to maintain. Terraform provides a much better solution. Let's go back to the official documentation and learn about count. So far, we've learned how Terraform can calculate values using expressions, functions, and conditional logic. But what if we need multiple resources instead of just one? Rather than copying and pasting the same resource block several times, Terraform provides a meta argument called count. According to the official documentation, count tells Terraform how many instances of a resource it should create. Instead of writing multiple resource blocks, we write the resource once and let Terraform repeat it for us. In this example, Terraform creates 4 resources from a single resource block. Each resource receives its own numeric index, starting at 0. Terraform automatically provides a special value called count.index. The first resource gets index 0, the second gets 1, then 2, and so on. We can use that index to generate unique names or configure each resource individually. Now that we understand what count does, let's apply it to our own project. Instead of deploying a single EC2 instance, we'll use count to create multiple instances from the same resource block. First, I'm going to comment out the example code we brought from the official Terraform documentation. We used it as a reference to understand how count works, but now we'll apply the concept to our own project. Now we need a way to control how many EC2 instances Terraform should create. Instead of hard coding the number directly inside the resource, we'll create a new variable called instance count. This makes the configuration more flexible because we can change the number of instances without modifying the resource block. Next, we'll define the value inside our dev.tfvrs file. For this example, we'll set the value to 2. That means Terraform should create 2 EC2 instances in our development environment. At this point, I made a small syntax mistake. I used instance count inside the resource, but Terraform doesn't recognize that as a valid resource argument. Instead of guessing, let's ask ChatGPT to explain the error and show us the smallest change required. ChatGPT explains that instance count is only the name of our variable. The actual Terraform meta argument is called count. So our variable provides the value, but the resource must use the official count keyword. ChatGPT also suggests using count.index to give each EC2 instance a unique name. Because count creates multiple instances from the same resource block, each one receives a numeric index. The first instance gets 0, the second gets 1, and so on. We'll add 1 to the index so the names start at 1 instead of 0. Now, Terraform will generate names such as Terraform-demo-development-1 and Terraform-demo-development-2. Before we continue, I'm going to comment out the monitoring line. We already used it to demonstrate conditional expressions. I don't want monitoring changes to appear in the next execution plan because our focus now is only on count and the creation of multiple instances. Keeping one concept at a time will make the plan much easier to understand. Now let's run Terraform again. This time, Terraform shows another error. The error says that our outputs are trying to access the EC2 instance as if it were still a single resource. ChatGPT explains that before using count, our resource represented one EC2 instance. That's why we could access the ID directly using aws_instance.ubuntu_server.id. But after adding count, the resource represents a collection of instances. Terraform now sees Ubuntu_server 0 and Ubuntu_server 1. Because of that, our outputs must either select one specific instance or collect the values from all of them. The star tells Terraform to collect the selected attribute from every EC2 instance created with count. Instead of returning one ID and one IP address, these outputs will now return lists containing the values for both instances. Terraform is now planning the changes required to manage two EC2 instances. Our existing resource has been converted into a counted resource, and Terraform can now track each instance using its numeric index. Let's review the plan carefully before applying anything. We should see two EC2 instance addresses. We can also see the unique name tag generated with count.index. The plan looks correct. Terraform will manage two EC2 instances from a single resource block. Let's apply the configuration. Terraform is now creating the additional instance and updating the existing resource addresses to work with count. Once the apply is complete, our outputs should display the IDs and private IP addresses for both EC2 instances. The apply completed successfully. Let's open the AWS console and verify the result. Here we can see both EC2 instances. They were created from the same Terraform resource block, but each one has its own unique name. This is the main benefit of count. Instead of duplicating the entire resource block, we define the resource once and let Terraform generate multiple instances dynamically. We now have cleaner code, less duplication, and a configuration that is much easier to scale. Count works very well when the resources are almost identical, but there is one important limitation. Terraform identifies these instances using numeric indexes. We currently have instance 0 and instance 1. These indexes are based on position, not on meaningful names. When the configuration becomes more complex, numeric indexes can make resources harder to identify and manage. For example, instead of instance 0 and instance 1, we may want named instances such as web and API. For that, Terraform provides another meta argument called for each. According to the official documentation, for each creates one resource instance for every item in a map or set. Unlike count, for each identifies resources using meaningful keys instead of numeric indexes. This makes the configuration more stable and easier to understand. Now let's replace count with for each. Instead of providing only the number of instances, we'll define a map that describes the instances we want to create. This will allow each instance to have a meaningful name and, later, its own configuration. We're replacing count with for each. The for each value comes from our instances map. Terraform will create one EC2 instance for every key in that map. Each dot key gives us the instance name, such as web or API. Each dot value gives us the configuration associated with that instance. In this case, we're reading the instance type from each value. Now, let's update our resource to use for each. The first change is replacing count with for each. Instead of telling Terraform how many resources to create, we're now giving it a collection of instances. Terraform will create one EC2 instance for every item in that collection. Here we're telling Terraform to iterate through the instances variable. Each item in that map will become one EC2 instance. You'll notice we're no longer using var.instance_type. Instead, we're using each dot value. Each dot value represents the current object Terraform is processing. In our case, each object contains the instance type for that specific EC2 instance. We're also replacing count.index with each dot key. The key is the name of the current instance in our map. In our example, those keys are web and API. Let's validate our changes. Oops, we found another error. This is actually expected. Earlier, when we introduced count, we also had to update our outputs because the resource was no longer a single EC2 instance. Now we've replaced count with for each, and the resource type has changed once again. Since we're now using for each, our resources are stored as a map instead of a list. That means we need to iterate through every EC2 instance and build a new output. This output will return the IDs of all the EC2 instances created by Terraform. The description simply explains what this output contains. Here we're creating a new map that Terraform will return after the deployment. This is called a for expression. Terraform will iterate through every EC2 instance created with for each. The variable name represents the key from our map. In our project, those keys are web and API. The variable instance represents the actual EC2 resource. For every EC2 instance, we're creating a key value pair. The key will be the instance name, and the value will be the EC2 instance ID. The final output will look something like this. The second output follows exactly the same idea. Once again, Terraform iterates through every EC2 instance. The only difference is that this time we're returning the private IP address instead of the instance ID. After the deployment, Terraform will display a map where each instance name is associated with its corresponding private IP address. This is one of the biggest advantages of for each. Instead of working with numeric indexes like 0 and 1, we can work with meaningful names like web and API. As our infrastructure grows, this makes the Terraform configuration much easier to read, maintain, and troubleshoot. We've updated our outputs, fixed the configuration, and Terraform is now ready to deploy. Let's apply these changes and see the final result. Terraform is now updating our infrastructure. Notice that we're still managing everything from a single resource block. The difference is that for each is now using meaningful keys instead of numeric indexes. Let's go to the AWS console and refresh the page. There they are. Our EC2 instances now have much more meaningful names. Instead of relying on numeric indexes, Terraform used the keys from our map to generate the resource names. This is much easier to understand than simply having instance 0 and instance 1. Finally, let's take a look at the outputs. Notice how the outputs changed as well. Instead of returning a list of values indexed by numbers, Terraform now returns a map. Each EC2 instance is identified by its key, making it immediately clear which ID and IP address belong to web and which belong to API. As your infrastructure grows, this makes your Terraform configuration much easier to read, maintain, and troubleshoot. We've now seen the two most common ways to create multiple resources, count and for each. Our configuration is much more flexible than before, but we still have some duplicated values. In the next section, we'll use locals to centralize common values and make our Terraform code even cleaner. Before we change the code, let's go back to the official Terraform documentation one more time. A local value allows us to define a reusable expression inside our configuration. Unlike input variables, locals are not provided by the user. They are calculated or grouped inside the Terraform project and reused wherever we need them. In our project, we repeat several tags across different resources. Instead of writing them multiple times, we'll define them once and reuse them. To keep the project organized, I'll create a new file called locals.tf. Terraform automatically loads every .tf file in the current directory, so we don't need to import this file manually. We're creating a local value called common_tags. It contains the tags shared by our EC2 instances and security group. Notice that locals can also contain expressions and functions. We're still using upper for the environment and lower for the managed by value. Now let's replace the duplicated tags inside the EC2 resource. We'll use the built-in merge function. The first value is our shared tag map, local.common_tags. The second map contains the name tag, which must remain unique for every instance. Terraform combines both maps into a single final tag configuration. This is how we reference a local value, local, followed by the local name. The name tag stays outside the common tags because it depends on the current for each key. We'll apply the same pattern to our security group. The shared tags come from local.common_tags, while the resource-specific name tag stays here. Now, if we need to change a common tag later, we only update it once inside locals.tf. Let's format and validate the project. Then we'll run a plan to confirm that our refactoring hasn't changed the intended infrastructure. Terraform may show a small tag update because our common tag map includes the project tag. Other than that, the infrastructure behavior remains the same. We changed how the code is organized, not what the project is designed to build. We've now transformed our original static project into a much more dynamic configuration. We used expressions to calculate values, string interpolation to build names, functions to transform data, conditional expressions to make decisions, count and for each to create multiple resources, and locals to eliminate duplicated values. The project is cleaner, easier to scale, and much easier to maintain. Terraform also supports dynamic blocks, which generate repeated nested blocks inside resources. We won't add them today because our current project doesn't need them, and forcing the example would make the configuration unnecessarily complex. We'll revisit dynamic blocks later when we work with resources where they provide a real benefit. Before finishing, here's today's AI tip. Once you understand the Terraform concepts, ask AI to review your configuration instead of writing it from scratch. For example, you can ask, review my Terraform project and identify duplicated values that could be moved to locals. Explain every suggestion before changing the code. This way, AI becomes a code reviewer that helps you improve your infrastructure as code while you stay in control of every change. The AI found several useful improvements. Some of them are immediate cleanup tasks, such as removing unused variables and stale values from our tfvars files. It also suggested more advanced refactoring, including centralized naming and fixed instance roles. Those suggestions are valid, but we're not going to apply all of them. Our current configuration is intentionally flexible because each environment can define different EC2 roles and instance types. This is an important part of using AI responsibly. We don't accept every suggestion automatically. We evaluate whether it improves our project without changing its intended behavior. After reviewing the suggestions, we'll keep our current for each structure and common tags local, but before uploading the code, I'll remove unused variables, clean the environment files, and correct the remaining descriptions. Terraform is now removing every resource it created and managed. Because all of these resources are tracked in the Terraform state, Terraform knows exactly what needs to be destroyed and in which order. After refreshing the AWS console, we can confirm that our EC2 instances have been removed. The security group created during this project has also been deleted. Today, we covered several important Terraform concepts. We learned how to build dynamic values using expressions and string interpolation. We used built-in functions to transform data. We introduced conditional expressions to make simple decisions. Then we learned the difference between count and for each for creating multiple resources. Finally, we use locals to eliminate duplicated values and make our configuration cleaner and easier to maintain. These are concepts you'll use in almost every real Terraform project. In the next episode, we'll explore one of the most important concepts in Terraform, state. We'll learn what the terraform.tf state file is, why Terraform depends on it, how it detects infrastructure drift, and how it tracks every resource it manages. If you've ever wondered how Terraform knows what already exists and what needs to change, that's exactly what we'll answer in the next episode. Thanks for watching, and I'll see you in the next video.